Okay, welcome to the lecture here. We'll get started in just a sec. We're going to continue on, finish up chapter 12. Then we'll roll into chapter 5, which should be nomenclature and all that good stuff. Okay, so we been talking about bonding and how to draw Lewis structures. We also got into obviously geometry towards the end last time. We're going to finish that up, like I said, and then we will roll into chapter 5. So just to review sort of where we were in terms of geometry. So when we do geometry, it's referred to as VSEPR, which basically stands for valence shell electron pair repulsion model, which is a long name there. That's why it's abbreviated. And excuse me. We started getting into some of the geometry, and again, it's basically related to the idea of electrons. So electrons are negatively charged, which means when electrons get near each other, they really don't want to be near each other. So they do their best to sort of get as far apart from each other as possible. And in the process of doing so, as they sort of escape each other, they will create sort of different three-dimensional geometries or shapes for particular molecules. The sort of degree to which they can sort of escape each other actually does depend on not only the electrons that are there, but really the type of electrons. So whether you're dealing with bonding and bonding electrons being near each other, which is kind of the best situation in terms of electrons, whether you're dealing with non-bonding and bonding electrons, so those would be like the dots and the lines on your structure, or if you're dealing with sort of the worst situation, which is actually non-bonding electrons near non-bonding electrons. So in your picture, that's essentially your dots near dots, and those guys really don't like to be near each other. So what ends up happening is they do definitely try to get as far away as possible. And what that affects is the overall shape of the actual molecule. So there's really two sorts of geometry names that we were talking about. One is what is referred to as the electron pair geometry. The electron pair geometry describes the three-dimensional arrangement of just the electrons around the central atom. And those could be bonding electrons, non-bonding electrons. And then we have the molecular geometry, which is also sometimes referred to as the shape. And in molecular geometry or the shape, that refers to taking into account all of the electrons, the bonding electrons, non-bonding electrons, the overall sort of three-dimensional shape of the molecule. And as we saw sort of last time, in certain cases, those names will be the same. And in the cases where those names will really be the same, both the electron group geometry, as it's put here, our electron pair geometry, and the molecular geometry, those both will be the same when we have no non-bonding electrons. So basically, when you draw your Lewis structure, if there's no dots on the central atom, pretty much both of those names will be exactly the same. The reason for that is that in that situation, we're dealing with only one type of electrons. We're only dealing with bonding electrons. So when we're only dealing with bonding electrons, because there's bonds everywhere, there's no non-bonding electrons, everybody's filled up with bonds. Both the electron pairs, how they arrange, and the overall shape of the molecule basically is the exact same thing. It's only when we start to get non-bonding electrons around the central atom, when you get dots on your Lewis structure, that we do get a difference. And the difference comes in only the molecular geometry name. So the electron pair geometry name is still based off of how many electron pairs you have. Again, doesn't matter if they're dots or lines. That name will remain the same. But the molecular shape will change. And the reason that happens is because we get those different interactions. We get the non-bonding electrons and the bonding electrons trying to get away from each other. We get the non-bonding electrons and non-bonding electrons also trying to get away from each other. And they're able to really get away from each other a little bit more because there's non-bonding electrons, which means they're not locked into place by a bond that's normally there. So as that bond is gone, that allows everybody else to basically move a little bit more, and we get these sort of different shapes or geometries that occur. The other really important thing when we're doing sort of geometry is, and only when you're doing geometry, when you go to the central atom, which is always the one you want to look at when you're doing geometry, you want to go there and count all double bonds and triple bonds. They count as really only one electron pair and one bond. So that's really important to keep in mind. Again, one electron pair and one bond for any double bond or triple bond when you're doing geometry. So that's, again, like I said, really kind of important there. So let's just kind of review the ones that we did go over here last time. So this is a situation when we have 3 or more atoms. By the way, we also talked about the idea of diatomic molecules. When we have diatomic molecules, which are only 2 atoms, basically, the geometry is always linear. So it doesn't matter, as we talked about last time, I think, single bond, double bond, triple bond, 2 of the same atoms, 2 different elements. It doesn't really matter if there's only 2. Geometry is always going to be linear. When we do get to 3 or more atoms, again, you want to go to the central guy. You want to look and count up how many electron pairs. So again, 2 electron pairs, and it also has 2 bonds, 1 and 2. So number of electron pairs is really what this is. Number of bonds would be 2. That's a kind of an easy way to remember it. And the electron geometry, electron pair geometry would be linear, and so would the molecular geometry, or the shape of it would also be linear. Basically, these bonding electrons get as far away as possible from each other, about 180 degrees from each other, and makes that linear shape. So again, here, when we look at the central atom, we don't have any dots. So both of these names are exactly the same. So 2 electron pairs, 2 bonds. Both the electron pair geometry and molecular geometry will be linear. We also saw one here where we had 3 electron pairs and 3 bonds. Again, the central atom important. 1, 2, 3 electron pairs, and also 1, 2, and 3 bonds. So 3 electron pairs and 3 bonds gives us what is known as trigonal planar for the electron pair geometry, and trigonal planar for the molecular geometry. Again, here, both of these names exactly the same, as the central atom here has no non-bonding electrons, so no dots around it when we draw the Lewis structure. So again, we're only dealing with bonding electrons, so both of those names will be exactly the same. This is also the one that sometimes people will call triangular, because as we talked about last time, it pretty much makes a triangle type shape, essentially. So triangular or trigonal planar, again, most people call it trigonal planar, but sometimes people still call it triangular because of that. Has a bond angle of 120 degrees. The bond angle does go with the electron pair geometry. So anything that's trigonal planar in terms of electron pair geometry will have a 120 degree bond angle, just like somebody was linear or had a 180 degree bond angle. We also saw another one here that had 3 electron pairs around the central atom towards the end. Again, 1, 2, and 3 electron pairs. And it had only, though, 1 and 2 bonds, so 3 electron pairs and 2 bonds. So here's where we're going to start to see a change in the names. The electron pair geometry here is still trigonal planar because it still has the 3 electron pairs. But what we now have is 2 types of interactions happening. We have bonding electrons and bonding electrons that want to get away from each other. We also have non-bonding electrons and bonding electrons, which don't like to be near each other even more, also trying to get away from each other. So what ends up happening, again, as I might have mentioned last time, because in a normal trigonal planar like we just saw, there's a bond here. Without that bond there basically locking everybody into place, it gives everybody a little bit more room to move. So the other 2 bonds have a little bit more room to really kind of move and bend. So that's why we get a different name for the molecular geometry here. I personally go with angular on this one. Some people will go with bent. And like I said, I think last time, people will sometimes go with bent angular. But I'm going to say for us, why don't we go with angular on this one? But people will still use bent. And there, I'll tell you why I will go a little bit different on this in just a second, why we're not maybe use bent for this particular one. And it really does has to do with the bond angle here. As you can see, the bond angle is 117 degrees. So it's a little bit more than what we have in our traditional trigonal planar, like we saw on the last slide, at 120 degrees. Again, 3 electron pairs, 3 bonds with that extra bond there, sort of locks these guys into 120. Without that bond here, in this particular example, and those non-bonding electrons, it's able to kind of move a little bit more. So we get that 117 degree in terms of the bond angle. Most people will, for this guy or something like this, will just simply go less than 120. So a lot of times people go just less than 120. Again, 117 in this particular example, but something less than 120 is typically where we would see sort of the bond angle go. Any questions on that stuff so far? I think that's the last one we left off on. Okay. So we're then going to go to sort of 4 electron pairs. So this is going to bring us a new sort of geometry here, which is tetrahedral. So again, when you look at the central atom here, always the important one, it has 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs. It also has 4 bonds. Yeah. So 4 electron pairs and 4 bonds. 4 electron pairs, electron pair geometry is what is known as tetrahedral. And that is this shape right here that we see. Kind of like a pyramid sort of deal on the bottom, a kind of triangle type shape on the sides of it when you kind of draw it in. And also with 4 electron pairs and 4 bonds, the molecular geometry name is also tetrahedral. So again here, both of these names exactly the same. The reason for that is no non-bonding electrons. So they're all bonding electrons, so both of these names are going to be the same. So again, as I mentioned earlier, when you draw your Lewis structure, got no dots, both of those names going to be identical, exact same name. Again, it's only the molecular geometry or the shape one that will change as we go through here. Bond angle is 109.5, which is your typical tetrahedral bond angle that occurs. You know, between these angles, about 109.5. And here is an example of methane. And again, like I said, it kind of makes almost like a pyramidal triangle type shape, and triangles on each of the faces on the bottom there when you look at it. I think there was a question last time. This is what is sometimes referred to as a space field model. And that's what a sort of space field model, usually like a computer generated sort of model. And I think somebody asked the other day as well, this is was sometimes referred to as like a ball and stick type model. If your question is it always tetrahedral, whenever you have 4 electron pairs and 4 bonds, there's 2 answers to that question. 4 electron pairs and 4 bonds like we have here, both of these names will always be tetrahedral. Once you have 4 electron pairs and maybe not 4 bonds, the electron pair geometry will always be tetrahedral. So electron pair geometry will always be tetrahedral whenever you have 4 electron pairs. The shape of it will also be tetrahedral when that goes with 4 bonds. And we're going to talk about what happens when we don't have 4 bonds here in just a second. So the electron pairs will stay the same, but the shape will differ. Other questions on that? So let's talk about another tetrahedral type geometry. Again, if we look at NH3, it has 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs. So it has 4 electron pairs. But here in NH3, it only has 1, 2, and 3 bonds. So it's got 3 bonds, which is 1 lone pair. So something with 4 electron pairs, the way that the electrons are arranged, as you can see in this picture, is still tetrahedral. So the electron pair geometry will still be tetrahedral. But what happens again is what would happen with SO2 is we do not have that 4th bond here in this geometry. and now has the non-bonding electrons near the bonding electrons. So what's going to happen is that's going to allow it to move a little bit more. And the shape that we actually get for this arrangement is what is known as trigonal pyramid or pyramidal. Most people call it trigonal pyramid. And as you can kind of see here, again, makes this pyramid sort of shape on the bottom there. And, again, kind of a triangle type pyramid type shape. And the bond angle here is less than 109.5, which is your traditional tetrahedral bond angle. And as you can say specifically here for NH3, it's 107. So tetrahedral with 4 electron pairs and 4 bonds has 109.5. Without that 4th bond here and that non-bonding electrons taking its place, gives it a little bit more room to move. So we end up with a bond angle of 107 in this particular case. Something like 107.3, I think, is the bond angle here. So again, what we see here is these two names change. They're not the same. The one that remains the same is the electron pair geometry with 4 electron pairs. Again, the molecular geometry or the shape here is the one that basically does change. So 4 electron pairs, 3 bonds, electron pair geometry, tetrahedral, molecular shape or geometry is trigonal pyramid. So trigonal pyramid, and this is a good point to talk about the other geometry that sounds like that, which is trigonal planar. Trigonal planar, as we just saw, is 3 electron pairs and 3 bonds. These two guys are not the same. They are different. So just don't write on your paper trigonal and hope for the best and let me choose, because I will choose wrong. Yes, so you do need to write trigonal planar or trigonal pyramid, not just trigonal, because there are 2 different ones. Also, don't write my other favorite thing that people do, trigonal. They're very confident there. And then, that type of deal. Like, oh, is it pyramid? Yes, that's what I wrote. Is it planar? That's what I meant there by the squiggly line and stuff like that. So there is a difference between those two, trigonal planar and trigonal pyramid. And you do need to definitely specify which one you're talking about. Again, don't just lay up the trigonal like is very common people will do. And let me choose or something like that, because I will choose with an X probably. Yes. All right. Any questions on that one there? So we have one last geometry, which also still has our 4 electron pairs happening. And that is something with 4 electron pairs and actually only 2 bonds. So that is like water here. Water has 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs, but has only 1 and 2 bonds. So something with 4 electron pairs and 2 bonds, because again, it still has technically 4 electron pairs. The electron pair geometry name is tetrahedral. But in this particular situation here, we actually have all 3 of the worst things happening in terms of electrons. We have bonding electrons near bonding electrons that don't want to be near each other. We have non-bonding electrons near bonding electrons, dots near lines, which don't like to be near each other. And the worst case scenario, which is non-bonding and non-bonding electrons that don't want to be near each other. So what ends up happening is those non-bonding electrons sort of go this way and spread out that way. As they do, our bonds sort of move as well. And what we get is a molecular geometry known as bent or V-shaped, is what some people sometimes call this, bent or V-shaped, as the molecular geometry are the shape. And in this particular case, we get a bond angle that's less than 109.5. We actually get something about 104.5 for water. So this is why earlier when we saw SO2, that for the molecular geometry, I personally go with angular. And I do that because this guy is doing a bond angle about 117 degrees. instead of bent or V-shaped, which is typically this bond angle, which is about 104 degrees. So it definitely is a difference between those two geometries. And that's why most people go angular or something bent angular, that angular is sort of in there with the SO2, again, to distinguish that. It really is more of a trigonal planar sort of geometry at 120-ish, less than that. While here, when we talk about bent or V-shaped, it really does go more with the tetrahedral arrangement, which is 109.5 or a little bit less than that in that type of thing. So again, that's why for the other one, I think angular is probably a better one to go with, and leave bent or V-shaped for something like water here, which it commonly is. Question on that there. So personally, I think the best way to kind of remember these is to memorize these. Obviously, like I mentioned before, a lot of people cannot kind of visualize all this stuff in sort of their head three-dimensionally. The easiest way, I think personally, is kind of number of electron pairs and bonds is kind of the easiest way to do that rather than lone pairs. The table here from your book does it more lone pairs than bonds. So whichever way you want to kind of do it, you can, but that's the best way to do it. That, I think, should cover all the geometries for our particular class. When you take 1A, you'll learn about a whole bunch more geometries that involve expanded octets and that type of stuff. Any questions on that there? All right, so let's take a look at sort of way you can predict the geometry. So we sort of talked about that. It really does involve sort of drawing a correct Lewis structure, including the non-bonding electrons. And again, it's always the central atom. That's the important thing when you're doing geometries. And again, our double bonds, triple bonds, counting as only one. So I think we drew some of these. So I'm just going to kind of quickly re-sketch some of these so we could kind of take a look at them. Hopefully I'll do it right here. We'll do that. I think this should look something like that. This guy, I think here, what we got there? We got 6, 12, 18. So do this one. So was that 18, I think. So we fill up all these guys. That's 16, that's 18. So we should lay up a double bond in there probably. If I drew that real quick. And this one I think we drew, or maybe looks something like this. And this guy. Okay, so let's take a look at each of these here and try to decide angles and all that good stuff and geometries. So if we take a look first off here at our HCN, again, central atoms, what you want to look at. So when we look at it, we're going to count electron pairs first. So this has 1 electron pair there. Our triple bond on the right only counts as 1. So that is 2 electron pairs. Also has 1 bond on the left. Triple bond only counts as 1 bond as well. So that's going to be 2 bonds. So something with 2 electron pairs and 2 bonds, the electron geometry is going to be linear. The molecular geometry will also be linear as well. So on our next one here, we want to count up electron pairs. So we got 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs. So this guy's got 4 electron pairs. In terms of bonds, it has 1 bond, just make them circles, 2 bonds, and 3 bonds. So that is 4 electron pairs and 3 bonds. So something with 4 electron pairs in terms of its electron pair geometry will be tetrahedral. Again, because it has 4 electron pairs. In terms of its bonds, though, because we have this non-bonding electron here, 4 electron pairs and only 3 bonds, is going to give us a molecular geometry of trigonal pyramid. Any questions on those so far? Coming over here to our SeO2, we got 1 electron pair, 2 electron pairs, again, double bond only counting as 1. And our non-bonding electrons is 3 electron pairs. So 3 electron pairs, but again, only 2 bonds, 1 and 2 there, making up circles there. So 2 bonds. So something with 3 electron pairs in terms of its electron pair name is going to be Trigonal Planar. Along with our 3 electron pairs and 2 bonds is going to give us a molecular geometry of angular or bent angular, whichever way you want to do it. Any question on those few so far? In terms of bond angle, let's just talk about those real quick before we finish the last 2, and I'll make some room to do that. Our HCN, which is linear and linear, should have a 180-degree bond angle. Our guy over here, which is tetrahedral and trigonal pyramid, because it is tetrahedral, but it has only 3 bonds, we will have something in terms of a bond angle of less than 109.5. So something very similar to NH3, maybe 107-ish, something like that. But something less than 109.5 would be our bond angle. And down here, this guy, again, has 3 electron pairs, which is trigonal planar. With that bond angle of those non-bonding electrons, we'll have less than 120 degrees. Again, something similar to SO2, maybe like 117-ish in that ballpark, but less than 120 should be sufficient. Any question on any of those so far here? Make some room. It got scribbled somewhere. Oops. All right, so let's take a look here at the last 2. We're going to do this one here. When we look at the central atom, it has one, 2, 3, 4 electron pairs. So it has 4 electron pairs. It also has 1, 2, 3, and 4 bonds. So something with 4 electron pairs and 4 bonds, if we go back to look at our geometry, is the same as this guy right here. It is tetrahedral, 4 electron pairs and 4 bonds, going to give us our tetrahedral geometry for both the electron pair geometry and the molecular geometry. So because there's no non-bonding electrons, electron pair geometry will be tetrahedral, and the molecular geometry will also be tetrahedral. That means the bond angle here will be 109.5 because the electron pair geometry is tetrahedral and we have no non-bonding electrons happening there. So tetrahedral on both of those. Again, no dots on the central atom. And that gives you the same name for both of those guys. And lastly here, if we look at this guy, central atom has 1 electron pair, 2 electron pairs, and again, our double bond only counts as 1, so that is 3 electron pairs. Also has 1, 2, 3 bonds. So 3 electron pairs and 3 bonds. Again, something with 3 electron pairs has an electron pair geometry of trigonal planar. And because it has no non-bonding electrons, the molecular geometry will be the exact same. So the molecular geometry will also be trigonal planar on that one as well. And it also will have a bond angle of 120 degrees, which is your typical tetrahedral arrangement. So when you're trying to do geometry, again, there are two different names. One's the electron pair geometry, and one is the molecular geometry. And again, you could do it based off of your Lewis structure. If the central atom has no dots on it when you draw it, both of those names will be the same. When it have dots, you'll have a different name for only the molecular geometry. You do have to sort of memorize that list of those geometries we just went through to help you sort of determine it. Question on that there? So why don't you take a second here, draw H2S and figure out its electron pair geometry and its molecular geometry and see what you come up with. Okay, so let's take a look here and just walk through the whole process from start to finish. So we have H2S. So again, when we want to draw the Lewis structure, we want to figure out the total number of valence electrons. So there's 2 hydrogens, each is 1. 1 sulfur, which is group 6. That is 8 valence electrons. Remember that hydrogen cannot be in the middle because it can only have 2 electrons. So logical arrangement here would look something like this. We're going to do one bond from the central atom to the outside atoms. That is 4 electrons. We're going to use the remaining electrons on the outside ones and fill them up. Since they are hydrogen, they are already filled. So once we fill up all the outside ones, then we go to the central atom and put them on as pairs. That would give us 2, 4. That's 8 total electrons that we put on there. Everybody has the octet rule met except for hydrogen, which has only 2, which is good. Sulfur in the middle has 8. So that would be the correct structure starting there. Question on the structure. Once we got the structure, it is always our center guy that is the most important in terms of geometry. So looking at our central atom, which is the sulfur, counting all of the electrons that are there, doesn't matter if they're bonding or non-bonding, has 1 electron pair there, 2 electron pairs there. This would be number 3, and this would be number 4. So this has 4 electron pairs. Now, the other important thing, in my opinion, is to count up how many bonds it has. So looking at it, bonds, it has 1 bond there, and this makes 2 bonds there. So the first type of geometry is the electron pair geometry. our electron group geometry, I called it in that table. And that is based on how many electron pairs there are. So something with 4 electron pairs means that the electron pair geometry is going to be tetrahedral. Now, when we talk about 4 electron pairs, we basically had 3 geometries that went with that. So in terms of the molecular geometry, we could also have something that had 4 bonds, which means it would also have a molecular geometry known as tetrahedral. We also had something with 3 bonds, which would have a molecular geometry of Trigonal Pyramid. And we also had something with 2 bonds, which would be bent or V-shaped. So these are all the 3 molecular geometries that go with a center atom that has 4 total electron pairs. So looking at this, we see that this particular guy has 2 bonds, which would take us down to here in terms of our molecular geometry. And that's because there are 2 non-bonding electron pairs present, which means those non-bonding electron pairs are going to try to get away as far as possible. And what's going to end up happening is our H's will bend downward, and our non-bonding electrons will go out in the opposite directions of each other. And we end up getting a molecular geometry, our shape of bent or V-shaped. And because of that, 4 electron pairs, and because we don't have 4 bonds and those non-bonding electrons, in terms of the bond angle for something like this, it would be less than 109.5, which is your typical tetrahedral bond arrangement. Any questions on how I got to all of those sort of answers there? I guess we should also answer what the actual question asked, which is, since I didn't read it, let me take a look. With the H2S, there are 4 electron groups. So that's basically 4 pairs or electron groups, however you want to call it, around the sulfur. And in terms of lone pairs, those are our non-bonding electrons. So there are 2 lone pairs. So it looks like D here would be the correct official answer here. The 2 lone pairs would be obviously these guys right here. 1 there and 1 there. Any questions on any of that there? Okay. So obviously we sort of jumped the gun here, but again, from our H2S, it is obviously going to be tetrahedral for our electron pair geometry. Again, I keep calling it pair. It's just what I learned. New way they call it group, but it's the same thing when I say pair or group. It again has those 4 electron pairs around the central atom, and the molecular geometry there going to be really bent or V-shaped. Right? It's a very common way that is referred to. And again, the bond angle here would be less than 109. So this probably wouldn't be the right answer. This wouldn't be the right answer. This wouldn't be the right answer. And again, the distinction between bent or V-shaped and angular is this distinction. 117 is angular, which is 3 electron pairs and 2 bonds. So this would have a bond angle very similar to what we see with water, which would be 104.5. I'm okay in this class if you go less than 109.5. They may want you to know the exact one when you get to 1A, but sometimes a lot of books will still just say less than 109.5 would be sufficient. Any questions on those there? And H2S would be a planar molecule based on its geometry, which basically means that they all sit sort of in a flat plane. And that's different than something like tetrahedral, where you have, for example, guys coming kind of out and back in terms of a tetrahedral geometry. They're not all in the same plane. Water and these guys will sit sort of all together within a plane. Any questions on that there? Okay. So let me just make sure of a couple of things here. Let's go like that. Let me just kind of put everything together in a table. And again, you do have sort of a table that's available to you in your book. But the best way to sort of do geometry and remember it is basically do this. We'll use this here. Go to perfect. Is when you have, again, three or more atoms involved and you want to do geometry, always look at the central atom. And really, like I said, usually the pretty easiest thing to do is the number of electron pairs, the number of bonds. And again, that will give you electron pair geometry name. Also give you a molecular geometry name, which again is sometimes is shape, and a bond angle. So 2 electron pairs, 2 bonds. Again, this is going to give you linear and linear. Both names the same because you'll have no dots on your Lewis structure. Bond angle will be 180 degrees. 3 electron pairs and 3 bonds will give you trigonal planar. Trigonal planar for both names. Again, you will have no non-bonding electrons. Bond angle 120 degrees. 4 electron pairs, 4 bonds will give you tetrahedral for both names. Again, no non-bonding electrons there. Will give you 109.5 degrees. Up until this point, when you draw all of your Lewis structures, there will be no dots on the central atom, all bonds. So no non-bonding electrons are dots. And again, both of these names are identical to each other. Now, when we start putting those dots in, like we saw, 4 electron pairs and 3 bonds. I'm sorry, let me skip one. Pop the right one there. 3 electron pairs and 2 bonds is what I meant to say. So 3 electron pairs and 2 bonds. Something with 3 electron pairs, again, for the electron geometry, still going to be trigonal planar. But because it has 1 electron pair that's non-bonding electrons, that is where we get our angular. And that is going to give us less than 120 degrees. We saw 117 as an example. When we get 4 electron pairs and on 3 bonds, that is going to give us tetrahedral for our electron pair geometry. Again, still has 4 electron pairs, but now we have, again, 1 non-bonding electron and 3 bonds. That's just the one that's going to give us our trigonal pyramid. And that is going to be less than 109.5. That's about the 107 degree one that we saw. And lastly, 4 electron pairs and 2 bonds. Again, 4 electron pairs still going to give us tetrahedral. But with those 2 electron pairs that are unbonded electrons bent are V-shaped. Going to give us less than 109.5. That's like the 104 one that we saw in terms of its bond angles. So these guys have non-bonding electrons, are dots. So this is sort of a table, and it's sort of similar to the table that you see in your book or that we were looking at. But this is really something you should memorize. It's the way you just do it. Memorize this many electron pairs, this many bonds. These are the numbers that go, are the names that go with it. and it's the best way to do it. And again, if you draw that Lewis structure, no dots, it's going to be the same name. If you draw it and you do see not dots, the electron pair geometry will remain the same, but the molecular geometry name will change. Question on that there. All right, now, one last thing in terms of geometry here before we finish up talking about it is, I'll draw it here, I think. Now, you can do geometry when you have, and it does happen occasionally, more than one central atom. So, for example, get rid of this. All right. So, for example, let's say I drew this guy here. So let's say I drew this one, which is known as ethanoic acid, also known as rubbing alcohol and all that good stuff. When we actually look at this particular molecule, there's actually one central atom right here. It's actually two central atoms right here. And believe it or not, there is 3 central atoms actually in this particular molecule. So when you do have more than one sort of central atom, you could do geometry for each of them separately. So what we typically do is, for example, we'll start here, we'll call this carbon 1, call this carbon 2, and we'll call that oxygen. So for example, if we were going to do carbon number 1, what we would essentially do is, a little hard to do online here, but essentially where I just drew that line to the right of it, we essentially would put our hand over the right-hand part of the molecule. And we would count how many electron pairs the carbon has, which would be 1, 2, 3, and 4, and how many bonds it has, which would also be 1, 2, 3, and we would count this guy over here, which would be 4 bonds. So the electron pair geometry for that first guy, because it has 4 electron pairs, should be tetrahedral. The molecular geometry should also be tetrahedral in that case, just for that first carbon, for carbon number 1 here. Yeah. Now, if we went to carbon number 2, what we would do is kind of the same thing. We would put our hand to the left of carbon number 2. We would also put our hand to the right of carbon number 2, and we would count how many electron pairs it has. Now, I kind of got rid of that one bond there, so let me pop it back in. So if we did, there would be 1 electron pair here, 2 electron pairs here, and the double bond would only count as 1 electron pair. So for carbon 2, we would have 3 electron pairs. Now, in terms of bonds, it would have 1 bond for the double bond, 2 bonds, and 3 bonds. 3 bonds. So in terms of carbon number 2, its electron pair geometry would be trigonal planar. And its molecular geometry will also be trigonal planar here, because it's basically 3 electron pairs, 3 bonds, no non-bonding electrons happening there. And then lastly, in this situation, we could go to our oxygen here, and we would want to count the electron pairs. So 1 electron pair, 2 electron pairs, 3 electron pairs, and it would also still have 4 electron pairs going in there. So it has 4 electron pairs. Has, though, only 1 bond and 2 bonds. So something with 4 electron pairs in terms of electron pair geometry is tetrahedral. But because we only have 2 bonds, the molecular geometry here would be bent or V-shaped? I scribble in the corner there, bent or V-shaped for that last one. So in this one molecule, at those three different points along the way, we actually have three different geometries happening. And if you actually built this in three-dimensional space, this guy would have a bond angle of 109.5 because it's tetrahedral. This guy would have more of a 120-degree bond angle. And lastly, this guy would have less than 109.5, which about 104-ish, give or take. So you would actually see the back end of this when you would build it. It would look something like this on the back end where the O and H would be. It would have this bent or V-shaped type of way. Question what you do if you have more than one central atom.
One question actually.
Yeah.
So, for the one to the very right, you said there are 4 electron pairs, and then for the one in the middle, you said there are 3 electron pairs. How come for the one in the middle, you didn't count the electrons around oxygen as the pairs?
So in terms of when you're doing geometry, it's only the central atom that's the important one. So in the case of the one in the middle, we're only interested in the carbon, basically. Yeah. So, and that's why we wouldn't count anything on the oxygen because it's not a central atom. So when we did go to the right of that, that oxygen though is considered a central atom. So that's why we counted the dots on that guy. And that's why we only looked at really the carbon on the far left as well, what was happening there. So you only want to focus in on whatever in that particular situation is the central atom, none of the other electron pairs. So when we talk about electron pairs or bonds, we're specifically talking about specifically around that central atom. Other questions? Okay. All right, so like I said, that sort of table I made, and again, it's very similar to the one that you'll find in your book. You know, it's really the best way to kind of do it is just to memorize it, draw your Lewis structure, and then obviously, you know, sort of identify the geometries based on it. All right, any questions on any of that there? All right. So finishing up, sort of talking here about sort of geometry and Lewis structures and bonding is what is referred to as a dipole moment. So I think we might have touched upon this a little bit earlier, but just to reiterate, a dipole moment basically goes with a polar molecule. And what it essentially means is, as a whole, that molecule is not sharing electrons equally, or they're not distributed equally along everybody that's in that molecule. And what that ends up doing is, if you do have a dipole moment and a polar molecule, it means that there is a part of that molecule that is more positive and there's a part that's more negative. The part that's more negative is the part that where the electrons are kind of heavily distributed, and the part that's more positive is where the electrons kind of move away from. Now, when we look at dipole moments or molecular polarity, it shouldn't be confused necessarily with what we saw earlier, which was bond polarity and using those electronegativity values. So when we use those electronegativity values, if you remember, that ran from 0 to 4, that helps us determine whether or not we have a polar bond, a nonpolar bond, or an ionic bond. And we can use those differences to help us determine if the molecule is polar as well. But when we do use electronegativity, it is really specifically between those two atoms, will those electrons be shared equally or unequally? Now, the place where bond polarity and molecular polarity are pretty much the same is when we have diatomic molecules, like we see here on the screen. So when we have diatomic molecules, when there's only really 2 atoms involved, that means in something like HF, there is only 1 bond. So because in this entire molecule, there's only 1 bond, we do need to simply just determine whether or not this bond is polar or nonpolar. And when we look at this bond, again, using that electronegativity, that's a 4 and like a 2.1, gives you something like a change in electronegativity of 1.9, which is a polar bond. We could draw that dipole arrow that points to the more electronegative atom that looks something like this. Now, because this particular guy only has one bond in the entire molecule, and the bond here is polar, this guy will also be a polar molecule. So this has both a polar bond and will be a polar molecule because the one and only bond that's there is polar. So diatomic molecules are really simple to sort of determine whether or not the actual molecule is going to be polar or nonpolar. And it's very simple. It is, if the bond that is there is a polar bond, we would expect the molecule to be polar. And if that bond is nonpolar, we would expect the molecule to be nonpolar. So if we looked at F2, they both have the same electronegativity of 4, which you can't see, and that gives us a difference in electronegativity of 0, which tells us this is a nonpolar bond. And again, in a molecule like F2, if that is the only bond that's present, we know that this molecule also would have to be nonpolar. So diatomic molecules, really molecular polarity and bond polarity will be the same because they only have one bond in the entire thing. Now, when we get to 3 or more atoms that are present, you do have to look at a couple of things. And I think what I'm going to do is skip ahead here and come back so I can just scribble some things. Yeah. So when you look at 3 or more atoms, you have to look at two things. You have to look at whether or not there are polar bonds. And again, that is your change in electronegativity values. And you have to look at the molecular geometry. So for example, a classic example, if we look at CO2 here, and if you look at CO2, this is what the Lewis structure should look like. And the first thing we want to determine is there polar bonds between carbon and oxygen? And you could do that by simply looking at the periodic table. You see carbon and oxygen are in the same period, but oxygen is further to the right, which would imply that oxygen should be more electronegative. And in fact, oxygen is more electronegative, so we would have a polar bond going between this one carbon and this one oxygen. And we'd also have one heading in the other direction between this carbon and oxygen. So the answer is yes, something like CO2 has polar bonds. So you may say, well, if it has polar bonds, it would make sense that the molecule itself should be polar. And you would be perhaps incorrect in this case because we do have to look at the molecular geometry. When we look at the central atom here, it has 2 electron pairs, and it also has 2 bonds. Again, double bonds counting as 1 electron pair and 1 bond. That means that the molecular geometry here is linear. So what that essentially means is CO2 is a straight line. And what we have essentially is an oxygen pulling one way, and then on the other hand, we have an oxygen pulling the other way. I am actually pulling on my pen here, if you look at the picture, and my pen is not going anywhere. And they essentially will cancel each other out in this particular case. And this molecule is actually going to be a nonpolar molecule. So CO2 is a really good example that you can have polar bonds, but because of the geometry of it, it will actually be nonpolar in this case. And that's because these bond dipoles, they are vectors, and vectors have direction and magnitude. And then I fell asleep in physics, but I woke up long enough to remember that in certain cases, they will add to each other. In other cases, they will basically subtract from each other. And basically, they will subtract from each other or cancel each other out when they go equal and opposite directions, or they head right at each other. In this case, equal and opposite directions, they will cancel each other out. Sometimes people think about this like pulling on a rope, like tug of war. So if you had two people pulling a rope equally in opposite directions, nothing's going to move. If you have somebody that pulls stronger in opposite directions, you know, it would move. So in this case, it would be non-polar. So just because something has polar bonds does not guarantee that the molecule itself will be polar, especially if you're dealing with 3 or more atoms. You do have to look at the molecular geometry. So if we look at something like water, which we've seen before, and if we look between water here and O and H in water, is it a polar bond? And oxygen is more electronegative. So if we drew our arrows, they would head towards the oxygen here, meaning the oxygen is more negative than the hydrogen. Now, in this particular case, it does have polar bonds. So yes to polar bonds like we were talking about before. The next thing we want to look at is the central atom and the geometry here. So our central atom has 4 electron pairs, and it has 2 bonds. So something with 4 electron pairs and 2 bonds, the molecular geometry, not the electron pair geometry, but the molecular geometry, is bent or V-shaped. So what's happening in this case, as I drew it here, kind of this bent shape, is we have, you know, if we had something like this, we have somebody coming towards the top, somebody else coming towards the top. They're going to actually meet in the top and kind of somebody pulled from the top. You can kind of imagine the whole thing would just kind of pull up and move. And this would make it a polar molecule, because what's going to happen is we will get what is referred to as a net dipole moment happening. In this direction, which means the oxygen side of water is more negative. The hydrogen side of water is more positive in this particular case. So just to show you how we get in this direction, I will try to remember physics here a little bit, but essentially when you have these vectors, you could draw them like this. This is our first vector. And then our second one, which is the guy coming the other way, you add it to the head of it. And then when these two come together, they actually add together heading in this direction. And that's how we actually get there in terms of vectors and that type of stuff, as opposed to, again, when we have things going in equal and opposite directions like we had in CO2, they essentially will cancel each other out as they are pulling equal to each other. Question on that. So when you're trying to determine molecular polarity, when you have 3 or more atoms, you could do these drawings, you could do these little vector moves and all these things, but who wants to really do that? Nobody wants to do that. So the better way sometimes is to look at it in terms of geometries. And there are certain geometries which are referred to as being symmetrical geometries. And what we're talking about here is molecular geometries. So we're talking about molecular geometries. So if you have a molecular geometry that is trigonal planar, and for our case, tetrahedral, what both of these guys have in common is, if you draw your Lewis structure, no non-bonding electrons on the central atom. So if you have these two geometries, no non-bonding electrons on the central atom, and most importantly, everything attached is the same atom or same element. So all the outside ones are the same element. It is a pretty safe bet to write this word right here. It is a nonpolar molecule. So if you have either one of those geometries and everything on the outside is exactly the same, going to be a nonpolar molecule. So for example, if we take CF4, I'm not going to draw all the electrons on the outside one, just this center guy. In this case, we do have polar bonds between carbon and fluorine. All of our arrows would head in these directions, heading towards the fluorine. The geometry here is tetrahedral, which means all of those fluorines are equal and opposites of each other. It means they are all pulling equal and opposites of each other. Nobody's going anywhere. And this guy would be a nonpolar molecule in this case. Now, what happens though, if I take one of those fluorines off and replace it with something like hydrogen? Well, we still have polar bonds heading towards our fluorines. And if you remember, the carbon-hydrogen bond is essentially a nonpolar bond. So what we have now is these three guys kind of pulling this way, and our carbon-hydrogen bond really not pulling the other way. And it actually is kind of helping a little bit this way, to be honest with you. And what you end up having is kind of everybody pulling in the same direction or pushing in the same direction. And you can kind of visualize the whole thing moving. And this will then go from a nonpolar molecule to a polar molecule in this case. So the quick way to sort of figure this out, if you have one of those two geometries, is if you have trigonal planar molecular geometry or tetrahedral, everybody on the outside is exactly the same element. Pretty safe bet to write nonpolar molecule. If you have trigonal planar or tetrahedral geometry and everybody on the outside is not the same element, it will most likely go from nonpolar to a polar molecule in that particular case. Question on those symmetrical geometries. That then leaves us unsymmetrical geometries. And for our class, unsymmetrical geometries will consist of and again, these are molecular geometries. So unsymmetrical geometries in our case would be our angular, our trigonal pyramid, and our bent, our V-shaped. And what all these guys have in common, if you draw the Lewis structure, is there are non-bonding electrons on the central atom. So you got dots on your central atom. So if you draw a Lewis structure and you see dots on the central atom and everything attached is the same element, it will most likely be a polar molecule. So dots on your central atom, everybody the same on the outside, going to most likely be a polar molecule. So again, that is how when we look at something like water that we saw earlier, I see dots on the central atom, I see everybody the same, going to be a polar molecule. Question on that there. What that really leaves you is linear, which is two electron pairs and two bonds. And in terms of linear, you do have to kind of look and see what's happening. So when you have linear, which is basically this, you could have something like CO2 where they're opposite and it would be nonpolar. But you could have something where everybody is kind of heading in the same direction and it could be a polar molecule. So linear is really the only one you have to figure out, but it is like a straight line. So if they go equal and opposites of each other, they will cancel. They go right onto each other head on, they'll cancel. They all go in the same direction. You know, it's like pulling one way more than another. So those are really the other ones you have to sort of worry about. question on that there? Okay, let's go back and see what we kind of skipped over, which should be what we were talking about here. All right, so again here, with this is our water. As I mentioned before, if you look at it, really the Lewis structure, the easy way to do it, dots on the central atom, everybody's the same, going to be polar. Again, possesses a more negative side on the oxygen, more positive on the hydrogen. As we'll talk about, it affects, if something is polar, it affects how it's able to interact with other things. It's able to interact well with ionic compounds, as we can see in these pictures, positive ion, negative ion. And because there's a negative side to water, the oxygen side of water will surround the ions and help something like sodium chloride, for example, dissolve in water. While water works okay with a negative ion as well, the positive side of water will surround it, which is the hydrogens. And what that essentially does is allow something like sodium chloride, for example, to dissolve. And that's why when we dissolve something like sodium chloride in water, it looks like it just disappeared. It's gone. It went away. It really didn't go away. It just got basically mixed into water's three-dimensional sort of network, and we can't visually see it anymore. It is also still there because it provides a nice way to separate out the ions, because without the water there, they would want to come back together very quickly and strongly. And we've seen that happen when you evaporate off water, for example. All the water gets out of the way and allows the two ions to come back together. You get your solid back. And why is the physical change? Nothing's really happening sort of chemically. It's just sort of hiding all the ions in the water network. Also involves things like hydrogen bonding that we'll talk about in a later chapter, how it's able to interact well with other polar molecules. All right, so we kind of talked about that. That's water. Here's CO2. Again, when we look at CO2, it is linear, does have polar bonds, but because it is basically a straight line and somebody's pulling to the right, somebody's pulling to the left equally, they cancel each other out. So these are what are referred to as space field models. The darker area here that's more red is more electrons, so more electron area. The kind of bluish area is a colder area, so that's less electrons. And that's why we say the hydrogen side of water is more positive. The oxygen side is more negative because of that sort of difference. So when you see those sort of color type models there, that's what it's sort of showing where the electrons are. And again, the darker red, more electrons present, the more blue, less electrons sort of present. And here we have sort of equal distribution of electrons. Again, you can kind of see equal electrons on both sides, kind of distributed here, equal sort of bluish area as well. So our CO2 will share the electrons a lot easily, no net dipole. So if it's a nonpolar molecule, there is no net dipole moment. So here's what we were talking about with symmetrical and unsymmetrical geometries. Again, if you look at your book there in that table, it's basically what we just talked about here. Here's our symmetrical geometries and sort of how our dipoles and vectors sort of cancel each other out. Again, in the tetrahedral way, everybody is equal and opposite. Same with our trigonal planar. So if we have the same guys, they're going to pull equal and opposites and cancel each other out in that particular case. So if we look at something like NH3, for example, which is sort of what we see here, if we look at NH3, here's how I would approach it, and you should probably as well. We go to the central atom. I see dots. I see everybody's the same. That means I got polar molecule, and that's what it would be in this particular case. So when you have that, because of that, dots that are there, and again, this was our water example, same sort of approach. Dots, everybody's the same, gonna be polar. So again, we have those unsymmetrical geometries, and they are a result of those non-bonding electrons basically being present. All right, so let's take a look at this one here. Polar or non-polar, take a second and decide. So this is probably as quick as you could do it, is what I would do. Central atom, I see no dots. Everything on the outside is the same. Going to be nonpolar. Symmetrical geometry, this is trigonal planar, triangle type geometry. So again, no dots, everybody the same, going to be nonpolar in this particular case. H2S that we drew earlier looks again something like this. So take a second, polar or non-polar on this one. So again here, I see dots. I see the same, going to be polar. So literally you could do it that fast, and as long as you do a correct Lewis structure, I would say probably 99% of the time you should probably be correct in your answer by just looking at that. I would definitely keep it that simple. Draw the right Lewis structure, look for either no dots or dots, everybody the same or not the same. And again, that will help you determine pretty quickly, you know, is the molecule polar or non-polar. So just to finish up here, let's just take a look at a couple here. Let's do... So let's do this guy. Let's do this one. Very bad double bond there. Let's do actually no, let's do this one I think we drew earlier as well. And let's just do this one as well. All right, take a minute or two and then we'll wrap it up here. And polar or non-polar molecule. So what is the molecular polarity on each of these, and see what you come up with. Okay, so again, I'm going to show you really sort of the quick way to do it. And again, like I said, probably in most cases, you'll be all right. Here's how I would do it. I would look at my correctly drawn Lewis structure, and I would go, I see a central atom, I see dots, and I see everything attached is the same. So that is an unsymmetrical geometry. That is going to give me a polar molecule. Again, what tells me that is I see dots is the first big clue. And again, everything's the same on the outside. Second big clue, always going to be polar in that sort of situation. Here I would go to the CO3. I would look at the central atom. I see no dots. I see everybody on the outside is the same. That's going to give me a symmetrical geometry. And that means that this guy is going to be nonpolar. And again, that is your trigonal planar, where everybody's going to be pulling at the corners here and cancel each other out. Over here, I would look at the central atom as CH4. Again, I see no dots. Everybody on the outside is the same. By the way, is carbon and hydrogen, which is nonpolar to begin with. That would tell me it is a nonpolar molecule. Here at NF3, I would look at the central atom. I see dots. I see everybody on the outside is the same. That is an unsymmetrical geometry, which should give me a polar molecule. And lastly here, I have N2, which is a diatomic molecule. Both of the ends in this case would have the same electronegativity, which means that this bond here, this triple bond I know, is a nonpolar bond. And because that is the only bond present in this guy, that would also mean that this guy should be a nonpolar molecule. Question on sort of how to determine molecular polarity here. And that's what we're talking about here. We're talking about as a whole, is this entire molecule sharing the electrons equally? Or are they sharing them unequally? And if they are sharing them equally, it would be a nonpolar molecule. Unequally would be a polar molecule. And that would imply that a polar molecule has a dipole moment, which basically means one side is more negative than the other side is more positive of the molecule. Any questions on any of that there?
Can you explain the nitrogens one more time, please?
The last one, the N2?
Yes, please.
Okay, yeah. So when we look at nitrogen, I'm just gonna, it's a triple bond, right? And it really doesn't matter if it's a triple bond or anything like that. But in this case, because it's a diatomic molecule, there really is only one bond in the entire molecule, which is basically the bond between the two nitrogens, which is that triple bond. And when we look at this bond that's there, they both would have the exact same electronegativity values if you went to that table. And basically, if you did the difference in electronegativity from that table, you would get a difference of 0. I don't know what the number is off the top of my head. Say it's like 3 or something like that. So basically, you take 3 minus 3, which would give you 0. And in terms of that bond itself, the individual bond between the two nitrogens, it has a difference of 0, which would be a nonpolar bond. Now, because this is a diatomic molecule, that one nonpolar bond is the only bond that's present in that particular molecule. And because the only bond present is nonpolar, the molecule itself would have to be nonpolar as well. So because it's a diatomic molecule, they're really the easiest to determine molecular polarity, and that's because it only contains one bond. Every diatomic molecule will have one bond, and because it only has one bond, you could just look at the bond itself and determine, is it a polar bond? Then the molecule has to be polar. Is the bond nonpolar? Then the molecule will be nonpolar. And that's different than all these other ones that we did on this page. There's not just one bond involved, there's multiple bonds involved, which is why we have to look at both all the bonds involved and the geometry that happens with that. But because in a diatomic molecule, there's just one bond and it's always linear, it's easy to determine. It's like basically a straight line, a pen or a pencil. So because that's the only bond that's there, if it's polar, it's going to be pushing or pulling towards one way than the other, and the pen will kind of move. It'll make it kind of a polar molecule. If that one bond that's there is nonpolar, they're going equal and opposites of each other, basically. you know, they're going to share the electrons equally. They're both pulling equally, and you can see my pen's not going anywhere. So they essentially cancel each other out. And that's why diatomic molecules are the easiest, because they're basically a straight line. So, and there's only one bond. So if you determine the bond polarity, you are also determining the molecular polarity. But it gets a little bit more complicated when we get more than one bond involved, like we have on the rest of them on this page. Other questions on that? Or any other questions in general? Okay, so that should wrap chapter 12. We definitely went a little bit long, so I'm sorry about that. So why don't we start lab at about 12:15, give everybody a chance to stand up and stretch, and we will be continuing on with the only today the one that we sort of started last time, or I said you could start on it. So it's the all this stuff, the bonding one basically. So I want to say activity 9, if I'm not mistaken, I think is what it should be. All right, so we'll open up the lab at 12:15, and we're kind of just going to be working on that. And if you have questions, obviously you could ask. So if you didn't put here in the chat, please do so, and I'll see everybody in about 15 minutes.